On a cosmic scale, stars are born alone. They ignite in isolation, burn for millions or billions of years, and die without ever touching another. But not all of them. Some stars are born in pairs. Binary systems, two giants chained by gravity, circling a common point in space. And when one of them ends its life, the other waits. And then, sometimes, they collide. The first thing to understand is that two stars rarely meet by accident. The universe is too empty. Even in the densest star clusters, the distance between stars is still hundreds of billions of kilometers. A direct collision by chance is nearly impossible. Most star collisions happen because they were already bound, already orbiting, already dancing toward an inevitable meeting. Binary systems lose energy over time. That energy goes out as gravitational waves ripples in space itself. As the waves carry energy away, the stars spiral inward, slowly at first, then faster. In the final moments, they move at a significant fraction of the speed of light, and then they touch. When two neutron stars collide, the event is called a kilonova. Neutron stars are the dead cores of massive stars that exploded as supernovae. They are not quite black holes, but they are close. A single neutron star packs more than the mass of our sun into a sphere the size of a city about 20 kilometers across. 1 teaspoon of neutron star material weighs 1 billion tons. Now imagine two of these objects, each with the density of an atomic nucleus, slamming into each other at relativistic speeds. The collision itself lasts less than 2 seconds. But in those 2 seconds, something extraordinary happens. The combined gravitational force rips both stars apart. Their matter does not behave like gas or plasma anymore. It becomes something called nuclear pasta, bizarre structures of protons and neutrons crushed into long cylinders or flat sheets, stronger than anything else in the universe. That material is then ejected in all directions. About 1 to 5% of the total mass. That might sound small, but a neutron star has roughly 1.5 times the mass of the Sunday. 1% of that is 10 Jupiter masses worth of material thrown into space in a fraction of a second. That ejected material expands outward at nearly the speed of light. It glows, not from heat alone, but from radioactive decay. As the neutron-rich debris expands, unstable heavy elements form and then decay, releasing energy in the form of light. That light peaks about 1 day after the collision and fades within a week. It shines hundreds of millions of times brighter than the Sunday. But here is the critical point. That light carries a signature, a specific pattern of colors that tells astronomers exactly what elements were created in the explosion. And those elements are the heaviest ones in the universe: gold, platinum, uranium, plutonium, thorium, iodine, europium. For decades, scientists did not know where these elements came from. Ordinary supernovae produce elements up to iron and nickel, but they cannot make gold. The fusion process in a dying star simply does not have enough energy to push past iron. Something else was needed. Something with an extreme excess of neutrons. Something exactly like a neutron-star collision. When two neutron stars merge, the neutron-rich environment allows for what is called rapid neutron capture, the R process. Atomic nuclei absorb neutrons so quickly that they have no time to decay. They just keep growing heavier and heavier until they become unstable and finally break down into stable heavy elements. Half of all elements heavier than iron are made this way. A single kilonova produces enough gold to equal several Earth masses. Enough uranium to power the radioactive decay inside terrestrial planets for billions of years. But the effects of a star collision are not limited to creating precious metals. The collision also produces a powerful jet. As the two neutron stars merge, they form a single object, either a more massive neutron star or a black hole. If a black hole forms, and it usually does, when the combined mass exceeds about 2.5 solar masses, that black hole immediately begins to spin. The leftover debris forms a hot, dense torus around the black hole. Magnetic fields twist, and then two narrow beams of material shoot out from the poles at 99.995% of the speed of light. These are relativistic jets. Those jets punch through the surrounding ejected material. They create gamma ray bursts, the most luminous electromagnetic events known in the universe. A gamma ray burst from a kilonova can outshine an entire galaxy for a few seconds. If one of those jets were pointed directly at Earth from a distance of a few thousand light years, it would strip away the ozone layer and cause a mass extinction. Fortunately, the nearest known neutron star pair is far enough away, but the power is real, measured, observed. The first confirmed detection of a neutron star collision happened on the 17th of August, 2017, an event named GW170817. Gravitational waves from the merger reached Earth first, detected by LIGO and Virgo. 1.7 seconds later, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst, the same event. Then telescopes around the world pointed at the same patch of sky in the galaxy, NGC 4993, about 130 million light years away. They saw the kilonova. They saw the light from newly created gold and platinum. For the first time, humans directly observed the birth of heavy elements in real time. That event changed astrophysics. It confirmed that short gamma ray bursts come from neutron star mergers. It confirmed that kilonovae are the primary source of our process elements. And it gave us the first multi-messenger observation of a cosmic event, both gravitational waves and light from the same source. A new way of seeing the universe. But neutron stars are not the only stars that can collide. White dwarfs can merge too. White dwarfs are the cores of stars like our sun after they exhaust their fuel. They are less dense than neutron stars, roughly Earth-sized instead of city-sized, but still incredibly dense. A white dwarf collision produces a different outcome. No gamma ray burst. No kilonova. Instead, something stranger happens. When two white dwarfs spiral together, their combined mass can exceed the Chandrasekhar limit, about 1.4 solar masses. That is the maximum stable mass for a white dwarf. Above that limit, carbon fusion ignites spontaneously throughout the entire star at once. Not in a controlled way, like in a normal star. All at the same time. This is a type Ia supernova, a thermonuclear explosion that completely destroys both stars. Nothing remains. No neutron star, no black hole. Just an expanding cloud of iron group elements and a blinding flash that can briefly outshine an entire galaxy. Type Ia supernovae are so consistent in their brightness that astronomers use them as standard candles to measure cosmic distances. They were the key evidence for dark energy. Without white dwarf collisions, we might never have discovered that the universe is expanding faster and faster. Now consider what happens to space itself during a star collision. The effect is not just the creation of elements or jets or light. The effect is also the production of gravitational waves. When two massive objects orbit each other, they stretch and compress space. These ripples travel outward at the speed of light, carrying energy with them. In a neutron star merger, the final seconds of the inspiral produce gravitational waves at frequencies humans can hear if we translate them into sound. The signal rises in pitch and volume as the stars spiral faster and faster, then cuts off abruptly when they merge. That sound is called a chirp. GW170817 produced a chirp that lasted about 100 seconds. In that time, the two neutron stars orbited each other thousands of times, each orbit taking less and less time until they were circling each other hundreds of times per second. The space between them was not empty. It was filled with intense magnetic fields, plasma, and radiation, and as they merged, space itself rang like a bell. That ringing persists. The black hole, or neutron star, left behind, continues to vibrate for fractions of a second, emitting gravitational waves as it settles into a stable shape. But the most profound effect of a star collision on space is not the waves, it is the enrichment. The heavy elements ejected from the merger travel outward and mix with the interstellar medium. They become part of molecular clouds. Those clouds collapse to form new stars. And around those stars, planets form from dust that contains gold, platinum, uranium, and iodine. Every atom of gold in your jewelry, every atom of uranium in a nuclear reactor, every atom of iodine in your thyroid gland. All of it came from violent collisions between dead stars. Without neutron star mergers, the universe would have no heavy elements beyond iron. No planets with metallic cores. No radioactive decay to keep planetary interiors warm. No gold for electronics. No silver for photography. No platinum for catalytic converters. The entire periodic table, from iron upward, exists because of rare cataclysmic events that last less than 2 seconds. There is one more effect. When two neutron stars merge, they sometimes do not immediately collapse into a black hole. Sometimes the remnant is a massive, rapidly spinning neutron star called a magnetar. Magnetars have magnetic fields 1,000 times stronger than ordinary neutron stars, a quadrillion times stronger than Earth's magnetic field. The magnetic energy in a magnetar alone is enough to power a kilonova for days. And if that magnetar later collapses into a black hole, a sudden change in magnetic field geometry can trigger a second burst of gamma rays. A delayed echo of the original collision. These echoes have been observed in some kilonovae. The light curve shows a bump, a secondary peak, days after the main event. That bump is the magnetar dumping its rotational energy into the expanding debris, heating it and making it glow again. Even in death, a star can die twice. So what does a star collision do to space? It fills space with heavy elements. It sends gravitational waves across the universe. It launches relativistic jets that travel for millions of years before fading. It creates black holes. It destroys two stars and gives birth to dozens of new elements. And in a very real sense, it makes life possible. Not because the collision itself is gentle. It is not. It is the most violent event since the Big Bang in terms of density and energy concentration. But because that violence creates the chemical diversity that complex chemistry requires, no gold, no electronics, no uranium, no plate tectonics, no iodine, no thyroid hormones. No thyroid hormones, no intelligent life. Every time you look at a piece of gold jewelry, you are looking at the frozen debris of a neutron star collision that happened hundreds of millions of years ago in the galaxy far away. Every time you measure time with a uranium-lead clock in geology, you are using the byproduct of two dead stars that found each other in the dark. Every time you touch something made of silver or platinum or tin or xenon, you are touching stardust from a collision so violent that it bent space itself. The universe does not make heavy elements quietly. It makes them in screams, in flashes, in chirps of gravitational waves that travel for 100 million years before a detector on Earth twitches by less than 1,000th of the width of a proton. Two stars collide, and the effect on space is not destruction, it is creation, the most powerful kind.